All right, welcome back. So it is Thursday, and this application I want to submit it on Friday. I can probably take more time than that, and to be honest, I think the possibility of me actually getting hired for this is a bit low. I just feel like there's going to be a lot of applicants, and I feel like this paper was intended to be read in no more than like an hour or two. Yeah, I will see, but, but yeah, I'm ready to close out, this whole, paper. So we've got, the last section here, well, second to last section is conclusion, but this is the principal findings, section. So I'll do one final, audio check here. The audio looks good. And close out this white paper on Thursday. And that'll give me all day on Friday to look at the other white papers, to look at some of the articles, and to submit my final email application. All right, so Section 3, Principal Findings. 3.1, Continuous Learning. CL learns incremental tasks with dynamic data distributions in various domains, including object detection and semantic segmentation, computer vision, NLP tasks, conditional generation, generative models, and autonomous driving, perception, motion planning, motion control, and user-vehicle interaction. One of the key challenges in continuous learning is to achieve an appropriate balance between stability and plasticity while ensuring adequate generalizability intra-task from training to test data, and inter-task, accommodating data distribution changes. Stability concerns LLM's memory as the difference between the task's current and maximum past performance, aka forgetting measure, and how learning a new task affects learned tasks, aka backward transfer. Plasticity is an LLM learning capacity defined as the extent to which the model cannot learn new tasks or the joint influence of learned tasks on learning the current task. The CL techniques working in embedding space, for example, soft prompting, adapters, and prefix tuning, are more expressive and effective than prompting, which operates on the discrete token space. However, most of the work described focuses on learning plasticity and intertask generalizability. The challenges of continuous learning of LLMs include multimodal learning. LLMs are pre-trained with enormous data sets that can pick up very complex and unexpected behaviors, for example, hallucinations. And I think there's more examples than that. Yeah. Real-world data are not restricted to a specific modality, but a random combination of multiple ones. Integrating and merging various modalities into a coherent continuous learning workflow requires efficient modalities, encoding, multimodal databases, assigning weights using fusions, and comprehensive benchmarks, which inevitably leads to increased computational costs without general performance guarantees. The second challenge of continuous learning of LLMs is data scaling and quality. And before I move to the next challenge, I'm just curious if I am correct to say that this is just one of the examples. So list some other examples, please. Okay, so it's working on that. That's okay. Takes it a while. I'll leave it some time. All right, so data scaling and quality is another challenge of continuous learning of LLMs. CL methods require task-specific datasets using sources similar to old tasks. The size and quality should adapt to obtain an appropriate trade-off between the efficiency and the effectiveness of learning incremental tasks. Inherent biases in training data can manifest in harmful or incorrect model decisions. Besides, the transferability of the task and domain-specific training data and their compositionality with, so like the way they're composed, I guess is what that means. I'll look it up. Compositionality. Oh. Okay, well, I guess it's a deeper meaning than that. Bottom up meaning determination. Okay, well, let's have the LLM unpack this whole thing, because that's kind of a deeper word than I thought it was. With other tasks and domains, without extra inference cost, and scalability issues in large scale training remain unsolved. Finally, effective and efficient CL methods may differ for smaller and larger models. Exploring scaling strategies that adapt and remain effective as the model size varies is crucial due to the ever-evolving landscape of LLM architectures. All right, so let's have it all unpack. Okay, so first, okay, so let's do unpack the term. Okay, we'll leave it to work on that. Think about that, and then read this. So yeah. There's plenty of other examples of unexpected or complex behaviors that can emerge from LLMs. As it says here, LLMs are pre-trained and can pick up very complex and unexpected behaviors, such as hallucinations. But there's more. They can get emergent reasoning skills. They can so without specific instruction, they can have more capability than the programming would suggest that they would have. They can adapt to context sensitive. They can adapt to the context. They can shift their tone, register, and dialect. So if the user's writing style suggests formality, the model knows how to respond formally, even though it's never been directed to do that. And that's interesting because, even like a person, right? It's like sometimes somebody with bad behavior wouldn't know to respond formally and might continue their, bad behavior even in the face of a formal response. So like that the model just like can do that is kind of interesting. Okay, and then there's hidden capabilities surfacing under certain prompts. So it can like invent new languages, or it can pick up new languages. There's like hidden capabilities that surface. Unintended bias or stereotyping. So this is where it can get a bit insidious. This is because they learn statistical correlations. They oftentimes reveal the real world biases behind the data they were fed. So a good example of that is the use of AI in like policing and crime. Oftentimes ends up being unethical because they draw correlations that aren't useful in actually solving crimes and are really only so I'll just leave it at that. Number 5, overly confident incorrectness. So hallucinated confidence. Yeah, that I've noticed that one. That's a big one. That's definitely a big one. So yeah, not only is um, yeah, so a hallucination. Not only is a hallucination bad, it's because it's one thing if it's just like, you ask somebody to do a difficult math problem, and essentially they're like hallucinating by getting it wrong because they're not doing the math right and they hallucinated a wrong answer. But then they can go back and double check and they can learn more. But if the model just doubles down, no, this is right, I'm 100% convinced it's right, and can't be convinced otherwise, uh, that is definitely a complex and unexpected behavior. Yeah, and then their moral, it appears as though they have values, which can be pliable and context dependent, and creativity and problem reinterpretation. Yeah, so they might seem as if they're doing cunning or lateral thinking, though it's just pattern based. So that's another way that they can have a complex and unexpected behavior. Is it seems as though they're uh, clever. All right, so let's learn more about this term, compositionality. Um, oh, okay. So it's the idea that complex structures or concepts can be formed by combining simpler constituent parts according to certain rules. So it's like related to the idea of emergence, I think. In other words, it's the principle that larger, more complex meanings or functions can be systematically built from smaller, well understood building blocks. Okay, yeah, yeah. Okay, so is this related to the idea of emergence? Yeah, I don't need to go into detail. I've got to get through this reading. All right, so the third challenge of continuous learning of LLMs is sustainability. The environmental impact of training and deploying LLMs is still at stake due to the enormous resources required. Future CL models and pipelines should be more energy efficient and operate in low resource environments to reduce environmental footprint and increase their accessibility. So, one of the things is it takes a lot of fresh water for AI development because artificial intelligence uses it for cooling their data centers. And then sometimes power plants use water. So basically, water um, is a finite resource, and our depletion of that finite resource increases the more sophisticated our current methods of AI become. So they're not very sustainable. Number 4 is trustworthiness. LLMs are susceptible to adversarial attacks. Modifying inputs can produce unexpected and harmful outputs. CL design should include encryption protocols for personal data and intermediate training and inference results without compromising performance. Improving CL models' robustness against such attacks is important, particularly for safety critical applications. Number 5, few shot generalization. LLMs struggle to learn tasks from few examples or domain specific knowledge. CL should improve its performance with limited training data. These data should be carefully selected as their distribution shift can degrade performance compared to previous data or cause poor model adaptation. Number 6, multilingual learning. Making CL more accessible and effective in underrepresented languages with limited training data. That's interesting. Oh yeah, so that's a challenge of continual learning. Is underrepresented languages with limited training data are going to get left behind, and that's already we're already in a giant crisis, a biodiversity crisis. And that's extending to human diversity as well. There's a lot of there's yeah. So let's look at the biodiversity crisis in numbers. So, oh, this is interesting. They have a whole timeline. So 65 million years ago, asteroid impact in Mexico caused global classicism and rapid cooling, and the dinosaurs became. Let's see here. Wow, this is cool. This is a cool article. I'm not going to read the whole thing, but I just wanted to make the point that we're kind of in a interesting time in that um, uh, yeah. Well, I'm not finding a. Uh, okay, this I'm not sure if I'm probably just feeding to contra to confirmation bias here, but well, let's do this then. There is not a biodiversity crisis. Yeah, so okay, the AI will correct me on that. So yeah, there's. I'm surprised there's not like a Wikipedia on this or something. Because from what I understood, according to Nate Hoggins, like one of the most significant things that's happening right now is like the biodiversity crisis. Like we're like things are going extinct at a rate like they've never gone extinct before in history, and like we just don't have things anymore the way we used to. Like everything is becoming like instead of having an apple, a pear, a banana, a watermelon, we're gonna enter a world where we have apples and oranges, and that's all you get. And that's what's happening at a rate, further than it's faster than it's ever happened before throughout history. And it's not only happening with flora and fauna, it's also happening with human cultures as well. So AI could accelerate that potentially because underrepresented languages with limiting data are not accessible and effective in continual learning. They just get left behind. Number 7, responsiveness. The inference in CL should generate predictions in real time for applications such as chatbots or recommenders, where low latency responses are critical for user satisfaction. LLM inference efficiency is affected by the model size, increased computational costs of longer inputs, the number of requests, and dependencies on external knowledge sources. Rethinking what constitutes efficiency is necessary as additional parameters and representations are computed and stored. Current model compression techniques, such as pruning and quantization, solve the problem partially by focusing on the LLM's parameters representation, not their architectural elements. So the eighth challenge of continuous learning of LLMs is context size. CL uses a limited window of input tokens to generate subsequent words due to LLM's constrained context flow. This can cause difficulties processing lengthy sequences concerning coherence and relevance, since the model can neglect or lose track of the relevant information. For example, large document inputs or long conversations. Number 9, up-to-date knowledge. LLMs learn from data snapshots, and their knowledge is restricted to what is available on a particular date. Consequently, CL needs access to the most recent information. At the same time, updating LLMs with up-to-date knowledge may outdate their internal knowledge. Besides, managing conflicting knowledge from one or more sources to choose the correct one is non-trivial for LLMs and CL. For example, different data sets can contain contradictory information about the same fact or carry conflicting biases and inaccuracies. Since LLMs cannot naturally resolve such conflicts, external resolution strategies must assess the data's reliability. And number 10, which is the final challenge of continual learning for LLMs, is unified benchmarking. Various benchmark tools and datasets make it difficult to reliably compare the performance of different methods and algorithms against a standard set of tasks and metrics. If the metric is the goal, it may not continue to be a good metric. There is no guarantee the benchmark data was not used for LLM training directly or indirectly. Moreover, the performance against research benchmarks does not necessarily imply usefulness in a real-world setting. These may be small for industry standards, and the data can be very different. Open-ended evaluation is the biggest bottleneck to AI adoption, and current efforts focus on solutions that can be evaluated. Yeah, and you know, all of these benchmarks were just up and freely available on GitHub, and like a lot of these the data come for these LLMs come from scraping the internet, so you know, they almost certainly have the benchmark data. Well, maybe not the data is up on GitHub, but they definitely have the GitHub repos for the benchmark tests. Maybe not the results of the tests, but anyway, a recent study discovered that popular context-based parameter-efficient fine-tuning methods, including prompting, in-context learning, prompt tuning, and prefix tuning, are potentially less effective than full fine-tuning, even with the same number of learnable parameters. In particular, they have structural limitations when learning new attention patterns, since they cannot change the attention pattern over the content and can only drive the outputs of an attention layer in a fixed direction. Therefore, despite their success in learning tasks on the fly, they may be unable to learn novel tasks that require new attention patterns. All right, so that brings me to section 3.2, LLMs versus humans. LLMs engage in an iterative communication process, generating streams of tokens. They rely on underlying probabilistic models to produce token arrays in response to token arrays. When presented with an input token string, they utilize previously calculated weights to iteratively generate and return a token stream that aligns with the input based on a certain probability threshold. This communication is constrained by the maximum number of tokens LLMs accepted. I found another typo. Accepted at once, context size, to generate a self-contained output. External data can be incorporated as vector embeddings and query vector databases, VDs, to augment the trained model during inference. For example, retrieval augmented generation. So it being able to reach out and do a web search or access some database or something to facilitate its output. Mainstream LLM research focuses on improving capabilities within existing knowledge boundaries. Understanding the boundaries of their knowledge as limitations regarding the unknown, referred to as self-knowledge, is essential. Evaluating 20 available LLM self-knowledge by measuring their ability to identify questions they do not know and cannot answer revealed a considerable gap between their capabilities and the human ability to recognize the limitations of their knowledge. Ooh, that's fun. While humans can quickly acquire new skills by leveraging prior experience or mental models as generalists, LLMs are still specialists performing well specific tasks. Oh, so let's do that. That could be fun. Um, okay. So you are standing. So imagine a room. Inside the room, you are standing with Ted. You are on one side of the room, and Ted is on the other. In the middle of the room, you see a table. On the table is a on the table is oh, let's see here, a TV monitor. You see the word Earth on the monitor. The monitor is facing you. It is parallel to the walls. You and Ted are opposite, are next to. Does Ted see the word on the monitor? Perspective and visibility of the monitor. So I'm assessing the monitor's positioning. It shows Earth and faces me, likely parallel to the walls to where Ted and I are positioned. This means Ted sees the monitor's back, not the word. That's interesting. So no, he wouldn't see it. Since the monitor. Okay, wow. So what are some unanswerable questions? So let's see, unanswerable questions. Okay, well we've got so what is consciousness? Let's ask it that. See, it does pretty good with questions like this because it'll say like consciousness is a concept that humans ponder about, and the latest research is here. So let me keep getting this reading done. Okay, so yeah, so while humans can quickly acquire new skills by leveraging their prior experience or mental models as generalists, LLMs are still specialists performing well specific tasks. Hyperparameters, for example, adapter size, LoRa's low rank adaptations rank, placement of added components, optimizer choice, and number of fine-tuned layers influence the CL performance. Performance ultimately depends on the manual tuning of hyperparameters, which requires a considerable effort. Automated optimization of hyperparameters is still an issue for the LLMs, lacking simpler solutions with better performance efficiency trade-offs. True wisdom is knowing what you don't know, by Confucius. So current ME approaches, which we remember ME was defined earlier. I forget what it was. I probably still have the. Oh. Oh, is ME mixture of experts? No, no. That's MOE. I forget what ME was. Uh. Uh. All right. Well, I think it's in a jargon table. I can look it up. So current ME approaches aim to make the existing model architectures more flexible to provide cost uh, efficient targeted updates without retraining the entire model. However, changing one model component can affect other components. Ensuring partial modifications do not reduce general performance or introduce algorithmic and data related biases is challenging. Vector databases are helpful as a cost efficient information retrieval solution within LLM's frameworks. However, they are still not optimized for retrieving the information with the intended meaning, such as incremental query adjustment and free text search using keywords in established retrieval paradigms. For example, relational and graph databases. So let me look at some of these old jargon tables. Um, yeah, see, it's good at these questions because it'll say, uh, right, like it'll talk about the fact that that it's still ongoing. So there should be, some of these should say jargon table on here. Yeah, so here's a jargon table. ME is hopefully on there. Yeah, model editing. So these are techniques or processes for adjusting an already deployed LLM to fix errors or incorporate new information without fully retaining it. ME focuses on carefully refining specific parts of the model's parameter or logic post development rather than retraining everything. And I think I remember a graphic that had to do with model editing. Anyway, yeah, so last paragraph. LLMs can store massive amounts of real world knowledge through intensive training. However, even with the existing incremental learning approaches, they still cannot update their knowledge fast enough to keep pace with constant external real world knowledge change and emergence. Accordingly, the incremental learning approaches described and existing solutions still need improvement concerning computational demands and effectiveness. Moreover, I know this. This one I feel like I know. Well, anyway, KGs mainly rely on textual graph structures to represent knowledge graphs. Yeah. Moreover, knowledge graphs mainly rely on textual graph structures to represent knowledge, whereas real world knowledge inherently comprises different modalities. Effective graph representations for multimodal knowledge that represent and align different modalities into coherent entities remain an issue for knowledge graphs. MLLMs, multimodal large language models, encode and align distinct modalities in a vectorial form. This gap between multimodal knowledge graphs and LLM representations hampers their synergy. All right, and I'm pretty sure KG is knowledge graph, but I should have it should be in one of the jargon tables I have. Not that one. I'm not sure. Well, I don't have all my jargon. You know what? Let's do this so we can search and we do jargon table. Oh, look at that! And now all of the jargon tables that I asked it to do are here. So we can open them all in a new tab. Not in a new tab. Well, not in a new tab, but that's okay. Uh, okay, so here's a jargon table. This is knowledge distillation, KD. I'm looking for KG. There it is, knowledge graph. So these are structured representations of entities and relations, useful for grounding LLM outputs and enabling symbolic reasoning. Integration with LLMs is still under development. These are neurosymbolic methods. This is what the current research is. So we got some papers on it right here. This would be a good one to read, but it's not part of the job application. But I feel like this is a very relevant paper, and it was published last year. It's a bit older of one with this research. This research moves at the speed of light, but might be interesting. Anyway, so yeah, I'm one page to go. Let's close it out. So LLMs and metacognition. LLMs can answer questions and generate useful content on a wide range of topics. And I just want to do a sanity check. Yes, it does stand for knowledge graph. Prompting techniques guide them to generate particular outputs in response to specific types of inputs. However, they expose shallow reasoning and are prone to errors as their complexity increases. They fail to address complex knowledge because they do not actually know how they learned to produce outputs. LLMs generate statistical responses emerging from numerical weights calculated at training time. Adapting their behaviors to continuously evolving knowledge is challenging for LLMs. This requires comprehensive and responsible guidance to incorporate emerging knowledge in a timely manner while conforming to ethical norms to ensure safe usage. The language modeling paradigm is based on the next token prediction, but its underlying structures and processes remain opaque. Thus, it is unclear whether current KE methods, that escapes me too, constitute meta learning stemming from variable probability distributions. Of training data. Therefore, achieving meaningful and intentional KE with LLM is questionable. For example, a failure in LLM's logical deduction is known as the reversal curse, where if a model is trained on a pattern A is B, it will not necessarily generalize in the reverse direction B is A. KE in LLMs may be more effective in task-specific scenarios where the consequences of model changes can be anticipated. All right, and let's see if KE made it into the... It did. It made it in. Cool. So this is knowledge editing, and these are methods to revise or update the internal knowledge of a LLM post-training to reflect new facts or correct mistakes. Approaches include model patching, LoRa editing, and memory-based updates. Awesome. That is very useful. So knowledge injection usually leads to overfitting LLMs as they struggle to obtain recent factual knowledge via unsupervised fine-tuning. A key challenge is the timely injection of relevant and updated knowledge in LLMs to develop user trust. Maintaining knowledge persistency in LLMs is another challenge, as their current knowledge is represented by generally non-persistent parametric memory and derived internal representations influenced by incoherent CL-CF trade-off, so continual learning - catastrophic forgetting trade-off. LLMs can sometimes solve reasoning problems, and they do so as a result of the token prediction process. In other words, reasoning problems are translated into pattern completion problems. Building trustworthy reasoning systems using LLMs means integrating them with a logic tool that implements causal mechanisms. Otherwise, we should be able to reverse engineer their responses to understand an internal process that leads to the reasoning driven response. Relatedly, the amount of LLM's generalizability corresponds to the extent of token prediction, which ultimately depends on the number of pre-trained parameters and dataset size. Although they optimize LLMs in terms of size and architecture to adapt to new knowledge, these issues persist in incremental learning. So, hallelujah, I am almost done with the first resource. Conclusion. Significant advancements have been made in developing specialized LLM-based systems to solve specific problems. However, the goals of generality and adaptability across multiple tasks remain an open problem. With its potential to bridge this gap, incremental learning holds the promise of enabling algorithms to acquire new knowledge over time, learn from limited data, transfer knowledge across tasks, and efficiently adapt to novel domains. The review investigated various incremental learning approaches in LLMs and have demonstrated promising results. Nevertheless, open problems and challenges remain, calling for further investigation. Periodic batch updates of LLMs do not reflect the real-time updates to the model. A key focus is on unifying various AI fields beyond LLMs. We can produce foundational advancements in incremental learning by integrating and collaborating across these fields. These advancements will enable more versatile algorithms that learn multiple tasks, generalize across domains, and continuously accumulate knowledge. This paper is a step forward in encouraging research in this direction by examining the current state of incremental learning in LLMs and highlighting the challenges and opportunities. We aim to inspire researchers and practitioners to explore synergies among AI research fields and contribute to the progress of incremental learning in solving complex real-world problems. So cool. That was good. Oh, and you know what? There was a abbreviations down here the whole time. So yeah, KG is a knowledge graph. Okay, so they're the same. Awesome. So that, I think that's the one that was really critical to read for the job application. There's a missing S. It says to read the white paper, but it doesn't say which white paper to read, and there are 3 white papers listed. But this is the long one, and this sounds like what AIGO is focusing on, the lack of incremental learning, or the ability to do that, especially in a truly real-time manner of LLMs. So I guess that one question would be, how does a let's see here. So down here in careers. So how does a heavy duty algorithmic how does a heavy duty algorithm that uses .NET Core / C# do incremental learning where systems that use 3 Mile Island don't? Like, how does that do it better? I guess that's definitely a question I'll add to my template. So let's grab the current state of the template, which is getting too big. So, well, I need to add that somewhere. Let me add it here. So I'm going to say, how does a duty rhythmic design using C#? How is a heavy duty algorithmic design using able to do continual learning where when so how is a heavy duty algorithmic design using .NET/C# able to do continual learning while the mainstream methods lag behind? Yeah, that I'm curious about that. Okay, so yeah, that's it. I did it. So I probably need to read a bit more than just that before I hand in, and I do need my 3 questions, and I do need my description of why I'd be good for the job. So I'm kind of not sure what to do. Next. So we've got concepts of skills. Oh, you know what? This might answer that question. So yeah, this might be a good one just because it might answer that question, and it looks like it's fairly short. Yeah, it's fairly short and readable. And like the other one, this has a full page of just citations. Huh. Cool. So these are interesting. This is another one that's similarly pretty short. All right, so yeah, these just look like pretty interesting. This one was, I think, the one that was critical to read to actually apply for the job. These are more just for curiosity. So I definitely will look at those. Let me see if I can just knock off some of these articles because they might be smaller. So then I'll just be able to check them off and focus on other things. Okay, so yeah, some are longer than others. So let's just do the really short ones. Okay, that's a really short one. That was a little bit longer. Very short. Longer. Longer. And probably the longest one. So okay, so there's some short ones. I'll knock those off. Yeah, and then I'll update my template. So I got my template here. Okay, so this one is done. And then let's try to get some of these other ones done. So I will read 3 of these and then mark those as done. So this is the insanity of large language models. So this one, mark is not done, and change it to be done when I finish reading it. This is imagine. And I should be using Obsidian for this. It'd be a lot better. All right, and then this one is what is AGI? Okay, so I'll go and read these. All right, starting with the insanity of huge language models. Microsoft is recommissioning the 3 Mile Island nuclear power plant in order to feeds with an extra S, just one of its next generation AI data centers. Anthropic's Anthropic AI's CEO predicts that we'll soon need models that cost 100 billion. Sam Altman is seeking 7 trillion to achieve AGI. Does this make sense? Yes, LLMs will continue to get better, faster, and cheaper. Yet they will not get us to AGI. Don't take my word for it. Jan LeCun, chief AI scientist at Data, says on the path toward AGI, an LLM is basically an off-ramp, a distraction, a dead end. So this is not just your person off the street. This is a significant. It's like Kobe Bryant saying that. What's that guy's name? Like he's too easy to defend. James Harden. All right, so deep learning is definitely not enough to solve AI, not by a long shot. So similarly, this is Dembis Hassabis, the CEO of Google DeepMind. And then the man of the hour himself, Sam Altman, CEO of OpenAI, even says, we need another breakthrough. Language models won't result in AGI. But I think when they say that, I think they're all kind of assuming that breakthrough will probably happen without that much difficulty. And it won't delay things that much. And it's not that because they've already had like a ton of breakthroughs, and it's not that they just need another breakthrough to get to. Oh, okay. Well, he's speaking to that to that specifically, which is good. So this is what Peter Ross says about that idea that they just need another breakthrough, which will be like shooting fish in a barrel. It's not that they just need another breakthrough to get to AGI. No, these limitations run much deeper. Apart from the inherent problem of hallucinations and lack of robust reasoning, the more serious and fundamental problem is that they cannot learn, update their core model incrementally in real time. This means that even a 100 billion model cannot adapt to new data and has to be thrown away on a regular basis, and a new model built from scratch. This limitation is dictated by the transformer technology that all LLMs are based on, and that is core to their impressive capabilities. GPT, generative, means it makes stuff up, pre-trained, read-only, transformer-based, requires bulk back propagation like training. Now consider that a child will learn language and basic reasoning with at most a few million words, not tens or 100s trillions of words. And let me get this claim evaluated by the very large language model that is being criticized. Okay, so evaluate this claim. This is my favorite prompt. And that's not to say that it always gets it right. You have to remain a skeptic. But I'm just curious to see what it has to say. So it's validating that claim. Yeah, so children from verbally rich households might hear, oh, okay, well, that's interesting. Well, yeah, well, ChatGPT hears trillions of words. Yeah, okay, universal. All right, interesting. I'll let it chug away at that. Also consider that our brains operate on about 20 watts. They don't need nuclear level power to build their model. Yeah, and that's something I don't feel like I need to fact check. I've heard that plenty of times, and it seems very believable to me. Um, my brains, especially, isn't exactly 3 Mile Island. Um, so yeah, 20 watts is all you get for human intelligence. So why do you need a 3 Mile Island for something not as good? So from first principles, we know that human level intelligence is possible with orders of magnitude less power and data. How can we achieve this with AI? The key is starting with a clear understanding of what makes human intelligence so powerful. This is a cognitive AI approach as opposed to big data statistical AI. Cognitive AI, also referred to by DARPA as the third wave of AI, starts with identifying the core requirements of human intelligence, which is fascinating. These include the ability to learn incrementally in real time, to learn conceptually, and this is what that whole paper we just read was all about. Yeah, so here's another interesting one. Cool. Yeah, this is interesting. To learn conceptually and to be able to learn from very limited data. For example, a child can learn to recognize, say, a giraffe with only a single picture exposure. We don't need hundreds of examples. We can also generalize situations with just a few examples and apply this knowledge in very diverse circumstances. This is called transfer learning. Importantly, we also monitor and control our thinking and reasoning via metacognition. We are able to think about our thinking. Yeah. So here's the factors in yeah, so the factors so here's a table, and the first column is factors. So one of the factors is what they focused on. The next is knowledge structure, training time, training supervision, data philosophy, training cost, train and operate on a laptop, hallucinates, needs human in loop, autonomous tool user, expandable, scrutable, catastrophic, forgetting risk, direct path to AGI. So the claim is that generative AI, the one we all know and presumably love at this point, I definitely decided to get the $200 tier. The claim is that they focused on accessing existing knowledge. The knowledge structure is statistical. Training time takes days or weeks. The training supervision is blind prediction, data philosophy, big data, quantity. Training cost is massive. Doesn't operate on a laptop. You need these giant data centers that use all of these precious resources like fresh water. They hallucinate. They need a human in the loop. Reinforcement learning from human feedback. They're not autonomous. They can't just use tools autonomously. They're not. You don't know how they work. They're a mysterious black box of weights, an inscrutable matrix. They experience catastrophic forgetting, and they are not a direct path to AGI, said so by Sam Altman himself. And the most laureled AI researchers working today. Some of the most laureled researchers working today also say that. But that's different from cognitive AI, and cognitive AI is what aigo.ai is all about. Cognitive AI, we're not focusing on existing knowledge, we're focusing on acquiring and applying knowledge skills dynamically. So, and that's what it's all about, right? It's like intelligence is you're trying to do new and novel things. Like we went to the moon, for the first time. So we wanted to do more things like that. The knowledge structure is conceptual. The training time is real time. It learns directly from experiences here and now, just like a human can. Training supervision. It's metacognitive. Training philosophy, small data, quality. Training cost, negligible. Trains and operates on a small device, a laptop, a phone, probably. Yes. Doesn't hallucinate. A human doesn't have to be in the loop, but can. It's negotiable. It's not a requirement. If there was no reinforcement learning from human feedback, the large ChatGPT would not nearly be as good. It probably wouldn't even be usable at all. Autonomous tool user, yes. Explainable, scrutable, yes. Doesn't forget, it's an elephant. And it's a direct path to AGI. So it sounds like cognitive AI is the way to go. And in fact, DARPA is saying that as well. DARPA seems to agree. INSA, Integrated Neuro-Symbolic Architecture, is a practical example of this cognitive AI approach, which promises to achieve AGI that will require many orders of magnitude less data and power for training, and that can learn and adapt continuously. No need to continually discard models and build new ones from scratch. A sane approach to AI. So this would be a great read. I would like, you know what, this is going to be part of the article, so I'll probably get to this at some point. All right, well, that's it for this one, so I'll mark that off. I'm going to mark this off as done here. And now I've got two more. I think I can get through them both. They're short enough. These two are very short, so let's quickly get through them. And then I will have to end the video. I don't have all day. It's already past an hour. Imagine an AI teaching itself to be a PhD level cancer researcher, and you can very easily imagine a human doing that. Well, I mean, honestly, you can't. Like, the human has to go to school, the human has to have professors, the human has to have books, but AGIs, so but we would consider a human teaching itself if it did all that. Probably. I don't know. And to be honest, you can imagine a human not going to school and just studying on its own over 10 years to have the knowledge of a PhD and then being awarded a like a celebratory degree for some major discovery or something. All right, so now imagine making 1 million copies of this. Imagine 1 million PhD level cancer researchers chipping away at the problem, pursuing different paths, and effectively coordinating their findings. Realize that AGIs have many advantages over other human researchers. So they work for dirt cheap. They copy themselves. They work round the clock. I don't know what this means. Oh, well, it says here. So they cost a lot less. They work dirt cheap. They can easily share knowledge. So it's not even about copying. It's they instantly share knowledge gained, and there's no egos getting in the way. They work 24/7 at full focus. They don't have certain highly desirable human distractions, so they don't get distracted. Humans really can't. So they don't, and it's not even about what the images show. It's just that they don't have hobbies or anything. They work 24/7 at full focus. Like that is like hard to imagine. They have photographic memory. They have direct, immediate access to all information in the world. They are much better at logical thinking than we are, which for humans is only an evolutionary afterthought. We're not very good at it. Exactly. Imagine the progress we'll make. Now replicate this across other problem domains: energy, pollution, nanotechnology, other diseases, aging, governance, etc. Naturally, research isn't the only area that will benefit from AGIs. Any cognitive desk-bound job can be replaced with a AGI, dramatically lowering the cost of goods and services, bringing about radical abundance. As AGI helps to fully develop selective robotics, physical labor jobs will also be automated. Human employment will become optional for everyone, allowing us to focus on things we want to pursue, be it raising children, arts, helping uplift others, or exploring the universe. That's a very optimistic view. I like it. Another application of AGI to enhance human flourishing is what I call a personal assistant. Almost everyone I talk to loves the idea: a super smart and useful AI characterized by 3 different meanings of personal. You own it. It serves your agenda, not some mega corporations. Hyper-personalized to you. It gets to know your history, goals, values, quirks, relationships, etc. Privacy. You decide what you want to share, with whom, and when. And it's important to note that I don't think ChatGPT is that. It belongs to OpenAI, which is basically Microsoft at this point. It has some capacity to store like a small memory, and you can give it customized prompts, but it has that catastrophic forgetting, and it's very, very bad at incremental learning and like real-time learning on the fly. So it really can't get to know it can't in real time learn your quirks very well, if at all. And then again, it's owned by OpenAI, which is basically Microsoft. So yeah, number 3 is not a thing. Such a wise, helpful AI companion will not only do the dirty work for us, like dealing with banks, insurance, utilities, etc., but will also help us make better decisions, help us think things through, and help us overcome difficulties in life. By helping us avoid decisions that we later regret, it makes us a better person. Yeah, and that's a big part of what I want the AI to do. Is almost like the idea of playing an RPG, hitting a quick save, trying something, and then loading the quick save if it doesn't work. You don't even need it can just make the decision for you, which is the best decision. And you got to make decisions like that, for instance, at every meal. What should you eat? The carnivore diet? It's like I want the AI to cook for me and serve me food based on the best science for health and longevity. Please, I will upgrade my ChatGPT subscription for that. Now let's move beyond imagining and help make this future happen using okay, so here's the answer to my question. How is it able to do it? Well, it's because they're using INSA, which I should read about. It sounds interesting. Well, I will read about. It's INSA. Okay, so I can mark that one done. That was a good one. Incredibly optimistic, but I like it. I think we need to be optimistic. I think it makes sense to be optimistic. Um, and yeah, there's still a long there's still yeah. I optimism is nice. What is AGI really, and how do we get there? There's a lot of confusion regarding AGI. In 2002, which is, oh wow, that's a big name, Goertzel. I used to spend hours and hours just watching him talk. This is Ben Goertzel. I think he's lives in Hong Kong, and I think he was born in Brazil. One of the best. What? Yeah. So, what can I say about? Oh, well, Epstein gave grants to like everyone. I don't think he was on the plane list. Oh, he's worked on Sophia. A lot of people have heard of Sophia. Um, uh, let's see here. Yeah, but anyways, this is kind of a a starstruck moment for me because I've definitely I didn't know that Peter Voss was so well connected to someone I admire so much and follow so closely online. And in fact, in 2002, they coined the term and wrote a book to describe its meaning and to detail potential approaches in achieving AGI. Unfortunately, the term has been much abused recently, often turning into simple marketing hype. When you have the CEO of a large LLM company saying that we'll have AGI soon, but it will change the world much less than we all think, he's not. Yeah, he's not talking about real AGI. Yeah, AGI will completely change the world, as we saw in the last one. Just imagine an employee giving full focus on something 24/7 for dirt cheap, and that employee is capable of teaching themselves to be a PhD researcher, cancer researcher. Like, they're gonna solve cancer. They're gonna figure out how to cure it. So what is real AGI? It is AI that can think, learn, and reason like humans, just be better. And honestly, like, you know, I feel like if we just understand like preventative measures better and like implement preventative measures better, like we can cure like we don't have smallpox anymore because it's because of the smallpox vaccine. And so it's like you don't even need to have a PhD researcher. You just need like a personalized assistant that can have people take preventative actions more effectively. Okay, so it is AI that can think, learn, and reason like humans, just better. They are systems that can learn in real time by themselves to reliably perform any cognitive task that a smart human can, including the discovery of new knowledge and solving novel problems. Additionally, they will be able to do this with minimal amounts of training data, time, and resources. With its ability to do cutting edge research and automate most tasks, real AGI will be of even greater benefit to humanity than electricity. Yeah, because you can just build your own electricity by having it tell you how to build a power generator or solar panel. It'll usher in an era of radical abundance. There is strong evidence as well as large and the counterpoint to that is, or it will destroy us all, because it will teach a 5-year-old how to make a nuke, and the 5-year-old will make a nuke and detonate it and destroy everything within its what radius, how large is a nuke. It will destroy everything within a half-mile radius. So, and that will just be completely vaporized. That's just for the immediate most severe damage zone. So let's say you're kind of naughty, bratty 13-year-old kid that has access to the LLM, lives in. I thought they were gonna let me look at the map. Well, anyway, that's the counterpoint to that is we'll have this wonderful utopia, or we'll just all immediately die. There is strong evidence as well as large scientific consensus that large language models, LLMs, by themselves will not get us to real AGI. They are inherently, by their nature, error prone. They hallucinate, cannot update their model in real time, and lack metacognition. They are black boxes, unable to meaningfully monitor or control their own outputs. Generative AI always needs a human in the loop to validate and tweak it. Finally, their insatiable need for data, CPU, and power is not ultimately economically feasible or sustainable. So on this graph, as real-time autonomous adaptive conceptual learning and reasoning increases, static so cognitive AI, AGI, human intelligence, LLMs. So LLMs, they don't get much more of that as their knowledge and skills increase, their static knowledge and skills. They don't get more real-time autonomous adaptive conceptual learning and reasoning. Cognitive AI does. Human intelligence has that quite a bit. So that's what we just read about, basically, is yeah. The answer is to be found in cognitive AI rather than generative or statistical AI. DARPA calls this cognition-based approach the third wave of AI. Current LLMs and other big data approaches belong to the second wave. Cognitive AI starts with a focus and deep understanding of what makes human intelligence so special, as opposed to we have a lot of data and compute, what can we do with it? It specifically engineers the core requirements of adaptive, conceptual, interactive, high-level intelligence. AGO, AGO, is that how you, I don't know. aigo.ai is one of only a handful of companies in the world with long-term experience with cognitive AI, which is awesome. And to our knowledge, the only one with a successful commercial product based on this approach. We have a detailed roadmap to scaling our technology to full AGI, leveraging our INSA, integrated neural symbolic architecture, that deeply integrates all the cognitive mechanisms required by human-level, human-like intelligence within one uniform architecture. Our goal is to utilize AGI to boost the flourishing of all humanity. We invite you to join us on this mission. So I'm hoping it doesn't turn out to be the case that this is the white paper that was meant to be read. I don't. So cognitive AI. No, these okay. So yeah, that's there's nothing like that in the white paper section. All right, so with that, knock those off. Those were pretty easy. Spent about an hour and 20 minutes, and when I come back, I'm gonna have the rest of these to go. But these are a lot less dry. It's not really an academic paper. It's just kind of more easy to read writing. So I should be able to get through these pretty fast, and I should have less like procrastination in doing these as well, because like today is like, I gotta finish reading this difficult paper. But I did so. So stay tuned for the next video where I close out the rest of the reading. I come up with the 3 questions to ask, and I think the 3 questions should be based a lot on the paper, and then I explain why I'm right for the job. So thanks for watching, and see you in the next video.